This week's lab is about titration. We've done titration before in 123, but we're going to focus on a few other things. So these are not our experimental goals, but this is the lab skills and the learning. The experimental goals you can get from the lab manual. So on lab skills, we want to learn how to work with a burette and getting a good endpoint, nice light pink endpoints. Also, we want to understand this concept of standardization. You're getting used to the fact that you come into lab and there's a chemical sitting on the bench and it's got a known concentration on it. That's not all that typical. Last week we saw that you can't just like take a colorimeter and plug it in and just measure absorbance and determine the concentration. The first task is that relationship between concentration and absorbance can change from day to day. So you had to standardize or calibrate that colorimeter by using known solutions and getting a graph and finding that relationship. That's calibration is kind of a form of standardization. Usually when we talk about standardization though, it's finding the concentration of a substance that is probably not stable. And very few things are stable. Even if I wanted to create a solution and put it on a bench and put a sticker on it and say it's this concentration, if I want to know that concentration to 4 significant figures, that's not realistic. It can sit there for months and be stable. It's going to change from day to day, week to week. In particular, acids and bases. One, if they can evaporate to some extent if they're not really well sealed, but also the chemicals themselves can react and oxidize and kind of change slightly over time. They can decay. So I don't know what the accurate concentration is unless I measure it. So when we are doing accurate work, we first need to take our substance, ignore what the label is, although the label gives us a good approximation, and we standardize it. We run some titrations on it, 3 or 4 titrations, and get a good known concentration of 4 significant figures. Also, we're going to do some learning of just making sure we understand the stoichiometric relationships. Do we understand the difference in titration between equivalence point and endpoint? The equivalence point is a stoichiometric concept where the endpoint is more of an experimental concept. And so ideally we make them match up, but they don't in particular. And part of that is how do we select an indicator? And then our calculations. Can you calculate moles of solution? Can you calculate molarity of solution? And can you relate moles of one thing to another in a chemical reaction? So titration again is I take a known substance where I know its amount and quantities and concentrations, and I react it with a substance that I don't know something about. I have to know what it is because I have to have a balanced reaction, but maybe I don't know the volume of it, or maybe I don't know its concentration. And I'm going to, from that relationship of saying, but I know the mole relationship of this reaction. If I reach stoichiometric ratio, so there's no extra of one or the other, they've all fully reacted, then I can relate the quantity of the known to the quantity of the unknown and use that relationship. So again, we'll talk about the titrant is the one that I do know, and the analyte is the one that I'm trying to figure out something about. Typically, it's the concentration that we're trying to figure out. Again, if I'm going to use stoichiometric relationships, I got to have a balanced chemical reaction. That becomes foremost important. Just a reminder, you probably are learning this in lecture, you probably are kind of in the middle of this or have passed it. Acids are acids because they produce protons. Of course, those protons immediately stick to water, so it's really present as hydronium ion, but we can refer to them as a general formula of HA or HX, meaning the A or the X is the other stuff, but they have to have proton in it for it to produce protons. So we usually begin that at the beginning of the chemical formula. There's a lot of organic acids that have many hydrogens in them, and some of them are acidic hydrogens that will deprotonate when they go into water, but other ones are not. So often we will put those hydrogens in the front of the chemical formula. The acidic hydrogens come first, so it makes it clear how many hydrogens could be produced. We also have these special titles: monoprotic acid, diprotic acid, and triprotic. Protic meaning proton, mono, di, tri meaning how many. So we'll call a monoprotic acid, again we say HA. Now that A might be Cl, it might be sulfuric It might be, so there could be all sorts of chemical substances that A is. It might be a very complicated benzoate formula, so it might be something very complex, but we just use A as a stand-in. And then we have diprotic would be 2 hydrogens and then some A, and triprotic is 3 hydrogens and some A. So A we can think of as almost like a variable. So there is no such substance called A. It's just a stand-in for the rest of it. Shortly you'll be learning that the rest of it is called the conjugate base, but until then we'll just call it A. And bases have a couple of definitions, but a common one is that they accept protons, and then they produce OH minus ion. So the general formula is going to be M, again, some metal, because it typically is, but it doesn't have to be. So some metal with OH. Now there are other kinds of bases. You'll learn about them later in the course. So we will usually, they don't get special titles, but the formula will be like something, some kind of metal with hydroxide, or 2 hydroxides, or 3 hydroxides. And we'll look at that. So we would need to understand that a general acid-base solution is I have something that's an acid with hydrogen, protic hydrogen, and I have something that's a base with hydroxide, and they're going to do a double displacement reaction, and I'm going to end up with an H and an OH, H plus and an OH minus, which is making the water, and then some other salt of whatever the A and whatever the M are. And of course, depending on the specifics of the chemical formulas, there might be 2 waters or 3 waters formed, and this chemical formulas change slightly. So you need to write that down. You need to be able to, given an acid and a base, be able to figure out what they're going to make and balance the reaction, because you need to know the coefficients of the acid and the base in this balanced reaction. If you don't, you're going to get in trouble, because sometimes it's a 1-to-1 reaction where there's 1 acid reacting with 1 base. If it's a monoprotic acid and there's 1 hydroxide ion in the base, then that works fine. But if not, you're going to get complicated because you're going to miss that stoichiometric step, and you're going to have the wrong coefficients, and you're not going to get the right answers. So it's important that we balance it to get those coefficients. All right, let's talk about the difference between equivalence point and endpoint. Equivalence point is sort of a theoretical construct that we can do in class, and it says equivalence point means there is no limiting reactant and no excess reactant. I have used 2 reactants, and I have used them in exactly the right quantity so that they're at stoichiometric ratio. If it's a 1 acid reacting with 2 bases, then I have gotten to the point where there's exactly twice as many moles of the base as there are of acid, and so everything has reacted to completion, and there's nothing extra, no extra reactants. So if that's true, if I have reached that equivalence point, then I can do calculations to figure out one from the other. If I know one of the moles, and I can multiply it by the coefficient ratios, I can figure out the other moles. That's the whole goal of what we're trying to do in titration. So that's where so it's a theoretical construct where I have equal stoichiometric quantities of 2 reactants. Again, in this particular case, this reaction is a 2 acid, HCl is the acid, and 1 base, CaOH2 is the base. And so at this equivalence point, I would have twice as many moles of HCl as I do of CaOH2. So you can try to figure it out, but again, it only takes one swap in your head where you switch the coefficients and you end up doubling when you really should have taken half. So it's easier to use dimensional analysis. You start with the one you know. So for instance, if I had calcium hydroxide titrated with HCl, and at equivalence point, I know that I had 18 moles of HCl in the flask. Then I could figure out how much calcium hydroxide had been in the flask. So 18 moles of hydrochloric acid, and then I would use again, HCl is what I'm starting with, so I want that coefficient on the bottom of the conversion factor and the 1 for the calcium hydroxide on the top. I have 9 moles of calcium hydroxide. Then I could go on to do more calculations with knowing the moles. Okay, but how do I know experimentally when I've reached endpoint? In other words, it's not like it's going to tell me, hey, we're all done, we're all reacted up, we're at stoichiometric ratio. They don't talk. I can't see them. So I have to use some experimental tricks. When we reach this point where something changes, we have to design a reaction where something changes to let me know. That's going to be our experimental endpoint. So how do we know when to stop adding that second reactant? So we start with an amount of one of the substances. It could be the analyte, but usually it's the analyte, but it could be the titrant. And we add the other one in a little bit at a time until I reach some magic point. We're going to use an indicator. And an indicator is a third chemical that's not in this reaction, but that can interact with one of the substances and does some kind of obvious change. Usually we use a color indicator that changes color to say, hey, we've reached this condition. So most of the time in a titration, we will use a pH indicator or something that will change. It reacts with either the proton or the hydroxide ion, often the proton. And when there's excess, it changes into a new state, which means it changes color. And we can also measure some properties. So we can be doing measurements on the solution as I'm adding it, and I'm looking for a certain property to be changed, like a pH or something like that. We're going to use pH for our equivalence point. If I have a strong acid, strong base reaction, then I will be at total neutrality when I reach this equivalence point. So I'm looking for, that's exactly at a pH of 7. If you are not reacting a strong acid, strong base, there's a weak acid or there's a weak base, this is not a truism, so be careful. You'll be doing that later on in chemistry too. So we're looking for a pH of 7. It turns out that if I have no extra acid and no extra base, I should be at pH 7. Everything's reacted. And at that point, I'm going to look for something that can tell me I've reached pH 7. And we're going to use this endpoint. We're going to use this indicator called phenolphthalein. So again, we observe using an indicator. So we have to add that indicator in. And of course, if you forget, it's not going to let you know. So we're going to add in phenolphthalein because phenolphthalein changes color at pH 8.2. We want to know when we're at pH 7. Now, I know that sounds crazy, that 7 to 8.2 seems like a big jump. It turns out there's a very small difference in concentration between pH 7 and pH 8.2. So it's pretty close to the equivalence point. It's not exactly the equivalence point, but it's going to let me know a little bit when I passed that equivalence point and turn pink. That's why we want the lightest pink, because we want to be closest to equivalence point. And there are other indicators that would be used for other kinds of chemical reactions. And we do see some of these, especially in biology, in cases where we're dealing with systems where the pH actually doesn't end up at 7. So again, let's go now talking a little bit of these chemicals, these calculations. We're going to be using a lot of these formulas the rest of this semester, and I just want to backtrack. Which equation I use to find moles depends on what my substance is. Most of what we're going to deal with in 124 is solutions. And for a solution, I'm going to use the molarity equation in one of two forms. If I'm trying to find moles, I use the rearranged version. Moles is molarity times volume, making sure that we have volume in liters. And then if I'm finding molarity, it's molarity is moles over liters. So we'll use those most of this semester. Occasionally, we'll have a pure solid. If I have a pure solid, then it's mass over molar mass. If I have a pure gas, I would use the gas law, ideal gas law, to calculate how many moles I have of it. We won't be dealing with gases this semester, though. So how do I calculate the concentration from my titration data? Again, this tends to be a 3-step process. Some people can confirm it into like a shorter one, but you have to be very careful that you're using it for the appropriate situation. So for titration, very often we have a known concentration, known volume reacting with another 2 solutions, and I'm trying to find the concentration. In that case, we first find the moles of titrant added. We know its concentration, molarity, and we know its volume that we added, so we use that to figure out the moles of titrant. Then we're going to use the coefficient ratio to determine how many moles of analyte I have. So that's the moles of titrant times the coefficient ratio. Make sure you're matching up. The titrant coefficient would go on the bottom and the analyte on the top. And then we'll use the molarity formula to figure out the molarity of the analyte. Moles that we just calculated in step 2 over the liters that we would have measured in the experiment. So you would need to know the molarity of the titrant and measure the volume of the titrant and the volume of the analyte. That's what we're going to be doing. So this is a sample calculation. I'm not going to work through it all. You can look through it in the notes, or you can pause the video, but it's kind of stepping through. This one's for an HCl NaOH reaction. If I want a one-step equation, which is pretty convenient, just make sure this only works for starting with a known concentration and I need to get a known concentration. I still need to know my balanced reaction. But here I can do some fancy. I know that the molarity is moles over liters for the analyte, but also for the titrant. I also know that on the top, this moles of analyte is the moles times the moles, if I knew the moles of titrant, times the coefficient of the analyte divided by the coefficient of the titrant. This is my step 2. So I could substitute that on the top of the fraction. I also know that the moles of titrant, which is there, is really the molarity of the titrant times the liter of the titrant. So I can kind of substitute the third step into the second step and the second step back into the first step, and I get this equation. And then I kind of rearrange it into not having a fraction, but into having a linear format, which means that I plug in the things that I know, and the one thing I don't know I can figure out. Notice that I have to have the coefficients in here. It looks like the dilution equation. It is not the dilution equation. In the dilution equation, I'm not doing a chemical reaction. There's no coefficients. It's just adding water. This one is a reaction. This is not M1V1 equals M2V2. This is coefficient of the other thing times the molarity of the base of one thing equals coefficient of the first thing times the molarity. So notice that the coefficients are opposite. So when I have the molarity of the acid and the volume of the acid, I'm multiplying it by the coefficient of the base. And same thing with the molarity of the base and the volume of the base, I multiply it by the coefficient of the acid. If you take this into account, you can kind of do this all in one step. So again, here I have a worked example with the one-step solution. And you see that this is what goes on. We are going to be doing in part B a calculation of the molar mass from titration data. So I can't use that one step because it doesn't have molar mass in there. So in that last step, the last examples, the last step was finding the molarity, and molarity is moles over liter. Molar mass is grams or mass over the moles. So it's grams of analyte over moles of analyte. So we're going to have to get there a little different. We're going to measure the grams of analyte, we're going to know the molarity of the titrant, and we're going to measure the volume of the titrant. We still do the first two steps the same. Find the moles of titrant from molarity times volume. Find the moles of the analyte by using the coefficient ratio. Then on the last step, I take the grams of analyte, which I experimentally measured, divided by the moles of analyte that I just figured in step 2, and I get the molar mass. Don't forget about standard deviation. So standard deviation, I've got the formula. We can come back to this in week 2. We'll talk about it more. But just understanding that the goal of standard deviation is saying, if you took a series of measurements, how close are they together or how far apart are they together? So we would need to get the average of those measurements and determine the deviation from the average for each individual measurement, dividing it by the number of trials minus 1, taking the square root, and I could report it related to the original average. So in this case, my average was 5.75 plus or minus 1.71 standard deviation. Not that great a job. 1.71 is almost a quarter of the 5.75. Speaking of which, two related calculations are percent relative standard deviation and percent relative error. Percent relative standard deviation is the standard deviation divided by the average. That gives us a sense of how big is the standard deviation in comparison to the number we were measuring. The relative error is about how accurate are you. And to do this, we have to have an accepted value. A lot of people make the mistake that they could trying to do this, but without an accepted value. And in our case, for instance, one of the problems that we will calculate this, but one of the problems is we don't have an accepted value. We're going to have to use an average for an accepted value, and that's going to come into play. We'll do that in week 2. Also, we can do something called part per thousand relative error. It's basically percent error. Percent means per 100. This is per 1,000. So when we're doing more precise work, a part per 1,000 error is going to be 10 times higher than the percent error. And that just allows us to sort of see a little bit more carefully small changes. So the only difference is I have my average value minus the trial value, and and I divide it by the average value. In this case, we're using the average as being the accepted value, and then I multiply it by 1,000. So I want to see for my individual trials, how close are they to the average? Ideally, all titration trials should have lower than 5 part per thousand error. If not, if they're all far away, it means you didn't do very good work. Like you're kind of sloppy and you're getting numbers all over the place. If one is particularly much higher than the others, it suggests something went wrong on just that one, and that may be an outlier. We're going to do a statistical test for outliers in week 2, and we'll come back to that and deciding. You can't just decide, I don't like this number, I'm going to get rid of it. That's not experimentally accepted. You have to have evidence to reject a data point, and we'll talk about how you accumulate that statistical evidence to do so. Again, in this case, we don't have the right answer, so for the accepted value, and I swapped the locations of these compared to the last slide, but we'll use the average value as the accepted value because we're going to do 3-4 trials. This is the standardization of NaOH. That's the first part. We get the NaOH, but we don't know exactly what it is. We need a 4 sig fig precision on it. So we're going to react the standardized NaOH with some HCl, which is fairly stable, that has been standardized. So we'll know the concentration of the HCl, and we'll do an HCl NaOH reaction. You've done these before, step through it, make sure you're looking at it. I might post a video of a good titration YouTube video for you if you need, but I think this is familiar for you. Again, take some time, make sure you're clear on what we need to do. Make sure when we're using the burettes, you're always taking the initial reading and the final reading and subtracting them to get our volumes. And then we're going to swap and find the molar mass of tartaric acid. So we won't use the HCl at all. We'll use that NaOH that we just standardized along with our unknown, in this case, will be tartaric acid, and we're going to weigh some out and do a titration with a solid, and then from that we'll get the evidence that we need to determine what the molar mass of tartaric acid is. And we'll do a lot of analysis and statistics on it in week 2. As we go, you've got some waste and how to report the standardization data. In order to do our standardization, to get a really good average, we're going to use our entire class's average. So I'm going to need, at the end of today's lab, you're going to have to put in the volume of HCl and the volume of NaOH you did for each of your 3 trials for part A, and I'm going to need you to put it in. I'll have a spreadsheet up where so if you need to type that in and let me know what those values are before you leave the lab so that I can have that to share with everybody. Thanks.